So we had talked about non-rotating black holes being a Schwarzschild black hole, and then there's equations that describe it. We call metrics. The Schwarzschild metric describes how space is stretched in the presence of a black hole. The closer you get to the black hole, the more space is stretched in that direction. So it takes a very long distance to get to the black hole. Well, Roy Kerr also figured out that a rotating black hole not only stretches space in the direction of travel towards the black hole, but this angular momentum also sort of holds on to the space as the black hole is rotating. Or has angular momentum. It's as if it's rotating. Though that's really hard to define how you actually rotate something that's got no size. But it's often referred to as a rotating black hole. So this is the kind of black hole that would actually grab space and stretch it around with the black hole. And so what does that mean? Well, it means that if you had a black hole and it's rotating that direction, if you measure the distance around a circle this way, you would actually get a different distance than if you measured around the other direction. And so the direction that you measure the circumference depends on the rotation of the black hole. And so it's kind of a weird thing that you go around one way, you measure one distance, you go around the other way, you measure a different distance. It has to do with how the black hole rotates. So your general description of the distortion of space due to a Schwarzschild black hole. The farther you go this way, you got to go. I can't just go straight. You got to go follow the curve, and so you go a whole lot farther than you would expect. Just to go that distance, you got to go that far, and so that's what that diagram tries to show. The farther you go, each of these lines is equally spaced, and so the going equal distances doesn't get you very far when you get up close to the black hole. Well, with a rotating black hole, the Kerr metric says that space is twisted around in the direction of the black hole. And so that means that you have to go farther around this way than you do the other direction. And so space is twisted in that fashion. And so that's an interesting thing because it means that if you go around one direction, there's no way you can possibly go fast enough to stay into orbit. And if you go around the other direction, there's no way you can go slow enough to stay into orbit. So that means if you're going around the right direction, you fall into the black hole. There's no option there. If you go in the other direction, you get thrown away from the black hole. There's no option there. And so what happens is that you get into this region of space where you have this frame dragging, what they call it, and space is twisted around. So if you're going the wrong direction, you get thrown outwards. So that means if something's spiraling into the black hole the wrong way, it'll spiral in and get thrown out with more energy than it came in with. That energy has to come from the black hole, and so that actually robs energy from the black hole when it does that. If you can follow the other direction, you fall into the black hole, which actually adds to the angular momentum of the black hole. A point singularity, can't carry angular momentum. So the singularity ends up expanding into a circle. A circle singularity actually has zero volume because it's got zero width. It's just got a diameter. And so it makes for an interesting thing. If you fall into the black hole from this direction, you're going to actually go into the singularity. If you fall from the north or south pole, you could actually go shooting through the singularity. Now, of course, you're still in the black hole, so you probably go bounce back and forth. Okay. The region of space near the black hole, where all this weird stretching of space happens and you can only fall into it one direction, we sometimes call the ergo region or the ergosphere. Ergo from the Latin for work. Because theoretically, if you shoot something into the black hole the wrong way, it's going to come out with more energy than you went in with. Which, those of y'all that remember from before spring break, when we were doing the class in person, I always had Star Trek references. And I remember that many, many years ago, I was watching Star Trek The Next Generation, and they had an episode where Romulan warbird had a malfunction in their engine core, and And we're not going to go through the whole story, but the key is that the way that they powered the Romulan warbirds was from a rotating singularity, injecting stuff into it. And I went, I understand how that works. Okay, it's a black hole thing. You put stuff in the wrong way and it comes out with more energy than it went in with. Measuring this distortion of space due to a rotating object. Yes, for a black hole, but remember, the sun rotates, the earth rotates. They also distort space. So NASA launched a spacecraft called Gravity Probe B back in 1994. And within a couple of years, it was able to measure the curvature of space, the distortion of space due to Earth's gravity. So that was able to be measured. Took another 5 years or so for analysis of the data to show that, sure enough, you have a tiny bit of frame dragging due to Earth's rotation. And so that actually verified that these relativistic effects that come from the Kerr metric really do happen. And so that really is happening with black holes. Measure with Earth, of course, but we can infer that would happen with a black hole. Now, how do you actually find a black hole? Well, it's not very easy. They don't shine. They're black. Light doesn't get away from them. Pretty much, if you had a black hole all by itself out there, it'd be really hard to find. Light might bend around it, but if there's nothing on the other side of it for light to bend past, you wouldn't even notice it. Space is black, black holes are black. I mean, how would you find it? Well, the key is that they're actually messy eaters. So if a black hole were near a star, then if the star expands and fills its Roche lobe, stuff's going to be falling into the black hole. Well, we know how this works. Stuff falling into anything doesn't fall straight in. It spirals in, makes an accretion disk. The accretion disk develops a magnetic field. Magnetic field causes stuff to spew in and out off the poles. So the stuff that doesn't actually hit the black hole directly, the black hole is tiny, so not a lot of stuff hits it, actually goes spewing out the jet. And so as much stuff goes, or more stuff goes spewing out the jet than actually goes into the black hole. And so the accretion disk, where all this stuff is spiraling in, is getting hotter and hotter and hotter, going around faster and faster and faster, and that is detectable. Likewise, this jet of stuff coming out would be detectable. And so as stuff spirals in, the accretion disk is what you would look for right here, because that's going to be getting hot. You get fusion going on the accretion disk and be giving off X-rays. And so that's what you look for is an anomalous X-ray source. Okay. You have to look at it from the right angle. If you look directly here this way, then the stuff spiraling in the accretion disk blocks your view. But if you look at the right angle, then you're going to be seeing X-rays coming from that accretion disk or from the jet that's being spewed outwards. Well, we actually found that in 1964. The star HDE 226868. This is the Henry Draper Extended Catalog. It's a blue supergiant, 30 solar masses. It's got a companion of 8.7 solar masses that orbit each other in a little under a week, about 5.6 days. Well, 8.7 solar masses is big enough to be a pretty bright star, except we don't see anything there. We just see a whole bunch of X-rays coming from it. And so the only thing, that means the object would have to be tiny. Well, the only thing that could be that much mass and that tiny would be a black hole. And so we're seeing the accretion of that black hole. Since then, we found at least 24 black holes. And that's mainly black holes that happen to be near stars and that are consuming stars as they exceed their accretion disk. As they see the Roche lobe and stuff goes accreting into the black hole. We've also found in the center of galaxies some black holes that are millions of solar masses or more. In fact, almost every galaxy that we can measure, the center of it has this giant, supersized black hole. And so we call these supersized black holes supermassive black holes. for a long time, that's all the black holes they knew about. Stellar mass black holes, which almost definitely come from stars that have collapsed. Supermassive black holes, they have to come from a different formation process because you can't have a million solar mass star. And likewise, it's not realistic to imagine millions of black holes running into each other to make this. And so there's got to be some of the process that makes it. So these are the only two types that we knew until not too terribly many years ago. They found a small number of intermediate mass black holes. Too big to be stellar black holes, but too small to be supermassive black holes. They've been found in certain globular clusters in small galaxies. So they probably form in a similar process to how supermassive black holes form. But this is our technique of finding black holes. News came out not that long ago of the Event Horizon Telescope, which is actually a radio telescope array that was studying the galaxy M87 and saw the shadow of the object at the center of it. There's a supermassive black hole in there, and we see the accretion disk around pretty much nothing. And so that is basically it's the shadow of the black hole. So that's the first, in the media it's referred to as the direct image of a black hole. It's not technically a direct image, but it is a mathematical construct of what an image would look like. And so that's the newest sort of cool news about black holes.